First Topos Institute Colloquium of the year. We're very happy to have Adrian Miranda talking to us about Kleisli constructions for pseudomonads. So, Adrian, please.
Thank you, David. Thanks for the introduction and thanks for the invitation. It's a pleasure to be here and to speak at the Topos Institute. Thanks also to everyone joining me here today or later, I guess, on YouTube. And so just a quick word before I get started. I'd prefer questions of a clarifying nature. You can just kind of throw them at me. And I'll also have certain parts of the talk where I'll pause to ask for questions. But other kinds of questions, suggestions for other things to think about or whatever else would probably be better, for after the talk. Okay, so the topic of today's talk, as David mentioned, was on Kleisli constructions for pseudomonads. So there are two kind of related preprints whose archive kind of code is there on the screen. So these are on enriched Kleisli objects for pseudomonads and tricategorical universal properties via enriched homotopy theory. Okay, so the plan for today's talk, I'll first review Kleisli constructions for monads, and we'll see that there are actually three different things that you could write down, even though these give isomorphic categories. The descriptions of these categories are indeed different. One of them perhaps is something that you might not have seen before, which will be interesting. And then we'll describe the analogous Kleisli constructions for pseudomonads as well. And we'll see that actually only the maybe less known one has nice kind of, enriched, an enriched universal property in the pseudomonad setting. So to bridge this gap, in part 3 of the talk, we'll also talk about some nice homotopical properties of the enriched Kleisli object, which allows us to relate it to other Kleisli constructions, such as the Kleisli bicategorical free pseudoalgebras. And then we'll talk about the tricategorical universal properties that these have. And then in the end, I'll talk about some further work and applications that have happened since all this. Okay, great. So let's get stuck into it. So Kleisli constructions for monads. And I'll first, on this pair of slides, give kind of an abstract description of these things. And then later we'll look at some concrete descriptions for Kleisli categories for monads. So the starting data is, of course, a monad, which I'm going to assume everyone's familiar with. And the problem that the Kleisli construction kind of solves is giving a universal adjunction splitting the monad. So in particular, you have an adjunction where when you kind of compose it, you get the original monad that you started off with. And it's universal in the sense that it's the initial adjunction giving rise to the monad. So for any other adjunction, also splitting the monad, you got this unique comparison functor from the Kleisli category. So all of that can be packaged in a nice abstract way in terms of a left Kahn extension. So your monad can be seen as a two functor out of the free living monad into cat. And then it's the left Kahn extension along kind of the inclusion of the free living monad into the free living adjunction. Given that it's a left Kahn extension, you can also write it down as a weighted colimit. So the Kleisli category for a monad is also the colimit of the monad weighted by a specific weight. So this weight is given explicitly over here. So you have the free living monad itself, which is delta plus. So finite totally ordered sets and order preserving maps, and then the monad acts by kind of +1 on this category. So that's the weight, and if you take this weighted colimit, you get the Kleisli category out of this. So that's the abstract description of the Kleisli category. Okay, I'll briefly say something about. Did I skip a? No. Okay, good. The Eilenberg-Moore construction as well. So this is just the limit variant. So now we want a universal adjunction, but what have I done? Oh dear. Okay, that's a mistake. It should be the other way around. It should be the terminal adjunction giving rise to the monad. So this K should be going in the other direction. Okay, but yeah, so this is now going to be a right Kahn extension of the same monad. And the reason that I mentioned this is just because to kind of remind everyone of the explicit description. So we have these algebras as our objects in the Eilenberg-Moore category, and these consist of maps from S of x back to your object x, satisfying these algebra laws. And then their morphisms are going to be the maps which commute with these algebra structures. Okay, so that's the Eilenberg-Moore construction, and that'll be relevant as well because it'll, of course, relate to one of the explicit descriptions of the Kleisli category. So Kleisli categories concretely, so this is all still kind of revision of things that, should perhaps be familiar to people, but just to remind everyone and get us all on the same page. Okay, so Kleisli constructions for monads concretely. So there are three different descriptions that you can give. So the first one, so in all of them, the objects are going to be the same as the objects of the category that you started off with. So in the first description, and this is actually the original description due to Kleisli himself. So a little bit of history, at that time, it was known that you could go from adjunctions to monads by just composing. But, it was kind of open whether you could go from a monad back to an adjunction. And this was actually the first solution to that problem given by Kleisli. And so in that description, we have, morphisms given by maps in your original category from X to S of Y. The unit for your monad gives the identity structure, and composition involves the multiplication of your monad as well, as written over there. So that's all well and good, and that's a nice description of Kleisli category. This variant of Kleisli categories, they're useful to describe, say, morphisms with generalized outputs. So this is one thing that you could use this formulation of Kleisli categories for. And of course, the dual versions, so co-Kleisli categories for comonads would give, morphisms with generalized inputs instead. Okay, so I won't be saying too much about the dual versions involving comonads, but of course, everything I say will dualize. Okay, so the second description of the Kleisli category consists of now morphisms of algebras between the free algebras on your object. So earlier we looked at the kind of Eilenberg-Moore adjunction, and the left adjoint sends an object to the algebra given by S of x, and the algebra structure map given by the multiplication of the monad. So these are algebra structures, and morphisms of algebras between them are now going to be the morphisms in this particular, or this second description of the Kleisli category. And finally, the third description is the one that perhaps you might not have seen. Very briefly, it's kind of explained on this slide, and I'll say a little bit more on the next slide. So this is going to have morphisms generated by those in A, as well as some formal algebra structures. So I'm writing it as epsilon x from Sx to x, and really this will be some kind of formal co-unit to complete the adjunction. And these should be respected by all other morphisms as though they were kind of algebra structures on X. Okay, so in a bit more detail. So this third description, so this is kind of given to us by the universal property that the Kleisli category should satisfy. So namely, it should have a functor from your base category and a natural transformation epsilon as drawn, which should be an algebra for the precomposition monad that you get by precomposing by the monad that you started off with. Okay, so given that it's a kind of universal solution to this problem, you can describe the Kleisli category just using this universal property in terms of generators and relations. And the third description that I'm talking about now really just comes directly from that universal property. So the generators, as I said, are going to be given by either morphisms from your original category. So these are, given to A sub s by the functor f sub s over here. But then you also have the components of this natural transformation, which are the new kind of generating morphisms epsilon x that I mentioned. Okay, and then the relations are exactly the things that say that this should be a formal algebra structure for the precomposition monad. And then also these epsilon, these components of epsilon should be a natural transformation. And so that gives this other relation over here. So the three relations come exactly from the universal property of the Kleisli category. Okay, so these are the three descriptions of Kleisli categories for monads. And as I said, later we will see that it's only this third one, the perhaps less well-known one, that has the kind of enriched universal property when we go to the two-dimensional setting. Okay, so, but before we do that, let's talk a little bit about the explicit kind of isomorphism of categories. So I said that all three of these are, deserve to be called the Kleisli category. And indeed, they're all isomorphic to one another. You may be familiar with the isomorphism between the Kleisli category given in terms of Kleisli maps and Kleisli composition, and the one given in terms of free algebras or morphisms between free algebras. But how is this third one related to the other two? Well, it's via what I've drawn on this slide. So we have, I'm just going to relate it to the Kleisli maps and Kleisli composition variant. So we send the kind of basic generators from our original category to exactly what you expect. This is what the left adjoint does in the Kleisli adjunction. But then we also have to send these formal counits to something, and they get sent to, well, the counits for the Kleisli adjunction in that description, and those are given by, this is a typo again, that should be the identity on S of X rather than the identity on X. Sorry about that. Okay, so that's what the functor in one direction does. What about in the other direction? So if we have a Kleisli morphism of this form, f from x to s of y, then we send that to, well, we just compose this with the formal counit to get back a morphism of the correct type, so something from x to y in the other description of the Kleisli category. And so this, you can check, is actually isomorphism of categories. Okay, so these all deserve to be called the Kleisli category because they are indeed just isomorphic to one another. But it is so these descriptions do diverge when we go to the two-dimensional setting. So I'll talk a little bit about that now. So the setting that I'd like to work in involves two categories, two functors, pseudonatural transformations, and modifications. If you're familiar with two-dimensional category theory, you might be wondering, okay, why not consider bicategories and pseudofunctors? Of course, that's a reasonable thing to do, and a lot of applications that you might come across will involve bicategories and pseudofunctors rather than two categories and two functors. But there is strictification that allows you to take those more complicated structures and replace them with simpler ones of this form. So I'll be focusing on two categories, two functors, pseudonatural transformations, and modifications. And this three-dimensional structure is often called gray. I'll talk a little bit more about the background that we'll need on that in a bit. But yeah, just to emphasize, so in a two category, the usual category axioms for, hold at the level of, 0 cells and 1 cell. So we have strict unit and associativity laws. And similarly for two functors, we have the usual functoriality laws holding, on the nose. But eta and mu, we're going to allow them to still be pseudo-natural transformations. So they'll obey the usual naturality laws up to isomorphism. And of course, these things are subject to further conditions as well. But now, in the context of a pseudomonad, we have the usual monad axioms also holding up to further data, which will be given by invertible modifications. So these are often written for, associativity, left unit and right unit by alpha, lambda, and rho. Okay, so these are subject to some axioms. In fact, you can get away with just two axioms, and I won't list them here, but I'll refer you to a paper of Marmolejo's from 1997 in which it's all written down explicitly. So this is what a pseudomonad is, and that's what we're going to be starting off with as our kind of starting data. Pseudoadjunctions generalize adjunctions in exactly kind of an analogous way. I won't go into details with that either, but you can write down the same type of extension problem. So starting off with a pseudomonad, you want to extend it to a pseudoadjunction, and you can choose whether you want to do that in a kind of terminal way or in an initial way. The terminal way will give you a Eilenberg-Moore object, and the initial way will give you a Kleisli object. That's kind of just by definition. But then in a paper of Steve Black's from 1999, he showed that actually the Eilenberg-Moore objects for pseudomonads can also be described as weighted limits in this setting of enriched over gray. And now these Eilenberg-Moore objects, so they're going to be two categories whose objects are going to be pseudoalgebras, whose morphisms are pseudomorphisms between them, and then you have some two cells which are often called pseudoalgebra transformations. I won't, again, go into too much detail about what exactly all that means, but suffice to say that pseudoalgebras are just kind of like algebras, but with the usual algebra laws holding up to invertible two cells subject to some further conditions, and similarly for pseudomorphisms. And then pseudoalgebra transformations are just the kind of the obvious thing that you would put between them. So you get a nice, well-defined two category out of these things, and indeed, this is the weighted limit in a similar kind of way, and solves that same kind of extension problem of extending the pseudomonad to a terminal pseudoadjunction. Okay, so that's Eilenberg-Moore objects for pseudomonads. And so far, it all seems fairly simple. Everything is just analogous to the one-dimensional setting. But when we go to the dual case, so for Kleisli constructions, remember there were three different descriptions that we gave. And so analogs of those descriptions can also be given in the two-dimensional setting. But if you take the description involving Kleisli maps and Kleisli composition, even if you started off with pseudomonad that I've been talking about, which has a base 2 category, base 2 functor, endo 2 functor, and pseudonatural transformations and invertible modifications, what you end up with using that description of the Kleisli or the analog of the Kleisli category there will only be a bi-category in the two-dimensional setting. So this is something which you get this weakness using this construction, and that means that this can't possibly be the enriched colimit because, well, it's only a bi-category. Whatever the enriched colimit is, it had better be a 2 category because it had better still be an object of gray. Okay, so this is not going to be the enriched colimit. However, in that same paper where this was introduced, so by Eugenia Cheng, Martin Hyland, and John Power, they did give a kind of universal property that is enjoyed by this Kleisli bicategory, namely a similar kind of thing. So it'll involve functor out of your base and pseudonatural transformation that gives a universal pseudoalgebra for the precomposition pseudomonad. So it's got a similar kind of flavor, but as I said, it can't be the weighted colimit. So what about the second description? So you might think that free pseudoalgebras should be the kind of a good kind of solution to this problem, which could plausibly be the weighted colimit, but that is not the case. And this was observed in a paper by Nicola Gambino and Gabriele Lobbia in 2021. So they observed that free pseudoalgebras are also not the enriched colimit. And the problem here is a bit more subtle. We want, if it were the enriched colimit, then this comparison that I've drawn on the bottom of this slide on the right over here should be an isomorphism of 2 categories. So it is indeed going to be a 2 functor, but it's only going to be a biequivalence instead of an isomorphism of 2 categories. So it's not it's not as strict as it needs to be, and hence it fails to be the kind of enriched colimit as well. So now for maybe more subtle reasons, but still it's not the enriched colimit. Okay, so this was, I think, where we were at. Yeah, that is all the background before kind of my work comes into the picture. I guess this slide is still background in some sense, but that was the state of play when I started thinking about Kleisli constructions for pseudomonads now a few years ago. I thought, okay, well, the two descriptions that we kind of know and love, they don't work. So what is the enriched colimit? What is the enriched Kleisli object for pseudomonads? And of course, such a enriched colimit needs to exist. Gray itself is co-complete, and so for just by standard enriched category theory, it'll have all kind of enriched colimits, and so in particular, it will have Kleisli objects for pseudomonads. But it wasn't obvious at that point to me what the how to describe the enriched Kleisli object for pseudomonads. But let's just before we dive into that, talk a little bit about the enrichment context that we are actually working in. So I've been calling this thing gray, but explicitly, so it's the category of small two categories and two functors with a tensor product given by the gray tensor product and with the unit given by the terminal two category. The gray tensor product is maybe a little bit more complicated. You can think of it as a homotopical version of the Cartesian product of two categories. And the example to keep in mind for your intuition is that the gray tensor product of the interval with itself, so the interval is just a one category, thought of as a two category with only identity two cells, and I'm taking the gray tensor product of that thing with itself, kind of just oriented in different ways so that we can see that we're going to get a square here. But that square is now, with the gray tensor product, only going to be commuting up to isomorphism. So there'll be an isomorphism thrown in over here. And so that's kind of what the gray tensor product does when it has components in different two categories. Rather than asserting a commutativity condition, as in the Cartesian product, it inserts a two-cell, an invertible two-cell there. Okay, so why is this thing interesting? Well, first of all, the internal Hom that you get exactly consists of the two functors, pseudonatural transformations, and modifications. So what I was calling gray earlier is really the self-enrichment of this structure. Okay. And I guess further things that might motivate interest in this is, of course, categories enriched over this context give a kind of semi-strict model of three-dimensional categories. So three-dimensional categories, tri-categories, and things are, of course, notoriously very complicated. But categories enriched over this structure are a lot less complicated. The only kind of weak aspect involved with them comes from this gray tensor product, which means that you have certain isomorphisms thrown in, but pretty much everything else, in fact, everything else is strict with them. Okay, so that's the enrichment context that we're working over. And I mean, this V is locally presentable, so we can describe colimits via generators and relations. So the third description that I gave earlier, the analog of that will kind of necessarily work in this context as well. So it's just a matter of kind of unpacking what that description gives us, and that'll be the enriched Kleisli object. Okay, so let me move forward and give that description. So again, the objects are just going to be the objects of the two category that you started off with. And the morphisms, now you're going to have two different, well, again, you're going to have two different kinds of generators. So given by morphisms in your original two category, but also these formal pseudoalgebra structure maps, which I'm writing as epsilon x again from S of x to x. Okay, so that's analogous to what we said earlier. Of course, now you're also going to have two cells given by the two cells in your original two category. But you also have some extra two-cell generators. And these will be the two cells mediating the pseudoalgebra structure. So mediating the usual algebra structure now as a pseudoalgebra. Okay, so I'm writing them as U of x and M of x over here. So there'll be certain generating two cells. And you also have what I've written over here as epsilon sub f. And this is really the pseudonaturality constraint of epsilon as well. So there will be three different kinds of generating two cells. I guess they're invertible generating two cells. Okay, and then these will be subject to the pseudoalgebra and pseudomorphism relations. So this is a description that you can give in terms of generators and relations of a two category, and it will, by construction, satisfy the appropriate kind of universal property in the enriched sense, in the kind of strict sense, everything up to isomorphism rather than biequivalence. So this is something that comes from just using kind of enriched category theory and working in a locally presentable setting. Okay, so now I'll talk about some of the results that we have about this enriched Kleisli object or pseudomonads. So as I said, it solves this extension problem. So you started off with a pseudomonad and you want to complete it to a pseudoadjunction in such a way that it's initial among pseudoadjunctions that split your pseudomonad. And now everything is kind of on the nose rather than up to some higher dimensional coherence. So when I say that the pseudoadjunction splits your pseudomonad, I really mean that when you compose it over, you get back exactly the same pseudomonad that you started off with. Okay, so it's solving that extension problem. And one of the things, okay, that maybe I should have mentioned earlier about Kleisli categories for monads is that the comparison from the Kleisli category, so just go back to the one-dimensional setting for a sec, the comparison from the Kleisli category is always going to be fully faithful. So that's something that holds in the one-dimensional setting. The analog over here is that, again, we're going to be able to say something about this comparison, but now it's going to be bi fully faithful. So what that means is that between Hom categories, it's going to be given by equivalences of categories. So that's a nice property that holds for the Kleisli 2 category, so the enriched Kleisli object for a pseudomonad. And really, this is, I mean, it might seem like it's just an interesting kind of fact, but really from this follows a lot of the rest of the things that we can say now about enriched Kleisli objects and the nice kind of homotopical properties that it has as well. So in particular, we can say, because this comparison is bifully faithful, that the following are equivalent. So there are going to be 3 conditions over here written on the right side of the screen. So if the left pseudoadjoint of the pseudoadjunction that you started off with is biessentially surjective an object, then the comparison is going to be, so that's one of the conditions. The second condition is, of course, this comparison being a biequivalence. And then the third condition is kind of the comparison that you get in terms of the universal property. So between the Homs over here, written on the bottom of the right hand side of the screen, that's going to be a biequivalence as well. So these 3 conditions are now equivalent to one another. And just to say, so biessentially surjective on objects is analogous to essential surjectivity on objects, but now it's up to equivalence rather than up to isomorphism. So we have an equivalence there between f of x and y. Okay, so that's really, I guess, the key results over here. So we can kind of characterize not when we, so in the one-dimensional setting, you can say that, a left adjoint is bijective on objects if and only if this comparison is an isomorphism. We don't have an analogous characterization of, when is pseudoadjunction the enriched, the enriched Kleisli object. But we can say when the comparison is going to be a biequivalence, and it's exactly these conditions. So even though I was kind of leading us down a direction of thinking about very strict kind of universal properties and investigating, enriched universal properties, somehow, if we want to be able to characterize these things in this nice way, namely just the biessentially surjective on objects left pseudoadjoints, then we need to allow ourselves this scope of thinking about universal properties in the kind of up to biequivalence sense as well. Okay, so that motivates then, well, okay, maybe before I go into that, it's high time for an example. And this example is really, it's quite a striking example. So let's think about the pseudomonad on the terminal 2 category. Okay, so it only has one object. And when you kind of unravel this description of the Kleisli, the enriched Kleisli object for this, you'll get that new generating morphism, which I'll just write as epsilon now. And then you'll get 2 generating 2 cells, which I've written as U and M. Of course, they'll be invertible as well. And these will satisfy the usual kind of monad laws. So the pseudoalgebra laws here become are pretty much the same as the monad laws that you would write down. Of course, the only difference being here that that U and M are invertible. So normally in a monad, you don't ask for the unit and multiplication to be invertible. We do have that here. But other than that, that's the description. And I mean, this is, so you would maybe have expected to just get the terminal 2 category again. That's not what you get. So this is what you get instead. So that's quite an interesting example there. And so the upshot is that, yeah, enriched Kleisli pseudoadjoints are actually not closed under composition. So if you did insist on kind of sticking to, everything being strict in the enriched setting up to isomorphism and all that, then you're not going to be able to characterize these left pseudoadjoints in any nice way. However, as I said, if you allow that kind of greater flexibility, so having this universal property up to biequivalence, then you can characterize them, and they're going to be exactly the biessentially surjective on objects two functors. So the left pseudomonads that are biessentially surjective on objects. Okay, and these are closed under composition. I mentioned this because closure under composition of left adjoints is a key kind of property used in the formal theory of monads part 2 in the investigation of things like REITs for monads. And so if we want to do analogous work in the two-dimensional setting, we're going to need to use this weaker kind of notion over here, which is only up to biequivalence. So this motivates the study of these weaker universal properties. Okay, so let's talk now about some nice universal properties of the Kleisli 2 categories for pseudomonads. So this is kind of almost dialogue that I was having with myself during my PhD now a few years ago. So, how do we make precise these weaker universal properties? And I guess the only real kind of way to do this justice is to use tricategorical notions of limits and colimits. So there's a notion of bicategorical limits and colimits, and there's a fairly well-developed theory relating these to nice kind of weights enriched over cat. And there should be an analogous story one dimension up relating tricategorical limits and colimits to nice weighted colimits over gray instead of over cat. But of course, that's a very complicated setting to try to kind of dive into. And it took me quite a while to work out the details of tricategorical limits and colimits, but we can kind of relate them in ways that you might expect to nice homotopical limits and colimits enriched over this particular monoidal category gray, but equipped with some kind of homotopy theory, and that's given to us by the Lac model structure. Okay, so I'll say very briefly something about what the Lac model structure is. So the fibrations lift adjoint equivalences and also isomorphisms in Hom categories. The weak equivalences are exactly these biequivalences, so the two functors that are biessentially surjective on objects and given by equivalences of categories between Homs. The cofibrin objects are also interesting to describe. Those are exactly the two categories whose underlying categories are going to be free on graphs. Okay. And I guess the most important thing from this slide, which will feature a bit later, is a description of the generating cofibrations. So there are 4 of them over here. So one of them is kind of the inclusion of the empty 2 category into the terminal 2 category. So things which have the bright lifting property against that are exactly the surjective on objects 2 functors. The second of these is as drawn over there, and the things that have the right lifting property against those are given by the 2 functors that are full on 1 cells.
Adrian?
Yep.
Sorry to interrupt, but I'm not sure we've ever had a talk about model categories before. We may or may not. So you might want to just give a little word of what you're going to use them for, and just like kind of how someone who hasn't thought of them before might see what you're doing here.
Yep. Okay, great. Thanks for that. So the idea is that model categories, without actually explicitly throwing in all the higher dimensional data that you might be interested in, they give you some structure on a category that allows you to talk about homotopy theory. And really for the purposes of what we're going to be talking about today, the things to think about would be these generating cofibrations that are on the right hand side of the screen here, and the idea is that we're going to want to be able to build. So on the next slide, what I'll be talking about is being able to build the weight for Kleisli objects for pseudomonads using these generating cofibrations. So using nice kinds of colimits and these generating cofibrations. So I think maybe that's all I want to say about model categories. But yeah, just for intuition, just think of it as a way of doing kind of higher dimensional category theory or homotopy theory, but without actually explicitly carrying around an infinite amount of data. Okay. Okay, cool. So these are the generating cofibrations, and as I said, they will be featuring in our construction of the weight. So I guess the main result here is that the weight for Kleisli objects is cofibrant in the projective model structure over here, and I guess I should say a little bit more on what that means. So this is an enriched functor category. So there's a gray category given by the free-living pseudomonad. That's what I've written here as PSMND. There's gray itself, so that's the self-enrichment. And this is just the enriched functor category, so there's nothing weak going on there. And so in an enriched functor category, in this nice setting that we're working with, we have something called the projective model structure. And that is given by, so the weak equivalences and the fibrations are going to be defined pointwise. So exactly those things that pointwise are given by the weak equivalences and fibrations in gray, which I described earlier. So pointwise biequivalences and pointwise things which are, lift adjoint equivalences and local isomorphisms. Okay, but then the rest of the model structure is going to be determined by that. So, okay, I should also mention, right, so the idea with model structures is that you have these three classes of morphisms, the weak equivalences, the fibrations, and then also this other class called the cofibrations. And the cofibrations can be you can work out what they are using the weak equivalences and fibrations, because they're exactly the maps that have the left lifting property against maps which are both fibrations and weak equivalences. So very briefly, that's what's going on here. So the takeaway is that cofibrations are going to be some complicated thing that you have to work out using this left lifting property. So they're not kind of explicitly given to us in any simple way, but they are kind of well defined via this left lifting property over here. Okay, so and the idea is that to show that the weight for Kleisli objects is cofibrant, what we need to do is we need to build it from the representable using particular kinds of constructions, and these constructions involve so push-outs of copowers of the generating cofibrations. Okay, so in particular, actually, in general, you're allowed to use even more constructions. I mean, I haven't used all of the generating cofibrations over here. I1 doesn't feature over here, but okay, and typically, you're also allowed to use retracts and things like transfinite composition, but we don't need that over here. So it's actually a lot simpler than what it could be. Okay, and I'm going to maybe just briefly describe, and this is more of an intuition pump than a full the full story. Indeed, it's only the first couple of steps in this construction. And really, the best way of describing how to do this is to describe the dual thing. So how do we build the Eilenberg-Moore? You can in fact even think about just categories here rather than two categories out of these special kinds of limits. So the kinds of limits that I'm going to be, in the first step at least, considering is just kind of an inserter. And so this inserter you can also write as a pullback of certain the pullback that's shown over there. And then the reason that I'm describing it in this way first is that it's going to be the exact dual construction that you need to do in the pre-sheaf category to the representable in order to build the weight. So the way that you can construct the Eilenberg-Moore category for a monad is that you kind of first universally insert this algebra structure map phi, okay, and then you say, well, actually, that needs to be an algebra structure map. So then you have to equify certain natural transformations which put in the unit law and the multiplication law for your algebras. Okay, so you would do an analogous construction to build the weight for Kleisli objects for monads in the pre-sheaf category. In the two-dimensional setting, it's going to be, again, analogous, but of course, there's going to be a couple of extra steps because we have so for a pseudoalgebra, we have extra data mediating the usual algebra laws. And so there's going to be some further steps involved there, but hopefully this conveys some of the intuition that we can actually build this weight using these kind of tools that we have at our disposal. And the upshot of all of that is to say that the weight for Kleisli objects for pseudomonads has nice kind of homotopical properties, namely that it's cofibrant in the projective model structure. So that's really the takeaway over there. And now I'll talk a little bit about tricategorical universal properties. So these are, genuinely quite complicated, but I could give an entire 50-minute talk just on this as well. But since this is not that, I'll just kind of emphasize the relevant aspects, the aspects that are going to be relevant to the story on Kleisli constructions for pseudomonads. But just a little bit of background. So these were, in general, they are given in terms of diagrams and weights, and the weight can be valued in bicat, so the three-dimensional structure consisting of bicategories, pseudofunctors, pseudonatural transformations, and modifications. And the explicit definition is on the left slide over there, and that was given by John Power in 2007. And there's been some work by Alexander Campbell in his PhD thesis, and then myself as well, which relates this to nice kind of weighted limits enriched over gray. And so what do I mean by nice? I mean that the HOMs of your two category A that you're taking the diagram and weight over, those should be cofibrant two categories. So remember I said that means that their underlying categories should be free on graphs, okay? And then also this, the weight itself, well, firstly, it should be a weight for an enriched colimit, so it should factorize through the inclusion of gray into bicat. But that factorization should have nice homotopical properties, namely be projective cofibrant. And so when you're in this setting, the nice thing that happens is that your enriched colimits are going to also have this more complicated tricategorical universal property. So in the tricategorical universal property that's kind of stated on the left-hand side of the screen, this involves much more complicated data. So trinatural transformations and tri-modifications, whereas the enriched setting, you only have strict maps in that setting. And so relating these two different universal properties is something of interest. And indeed, these more complicated things can be modeled using these nice kind of enriched things. Okay, so this is all analogous. You might have seen an analogous story in the two-dimensional setting where we have, bicategorical limits being modeled via, again, the flexibly weighted limits in the two-dimensional setting. So this is an analog of that one dimension up. So now we're doing kind of three-dimensional universal properties, and this is what we have there. Okay, so just to give a precise statement of the theorem. Okay, so we have that the gray enriched Kleisli object for a pseudomonad is also its tricategorical colimit weighted by the exact same weight. Of course, I didn't write this over there, but you explicitly have to take the inclusion of gray into bicat as well in order for that to be a weight for tricategorical colimits. But okay, so that's the universal property of the enriched Kleisli object. But of course, tricategorical colimits will be stable under biequivalence. So if I shift it via biequivalence, then that'll still be a tricategorical colimit. So this tells us that things like the Kleisli bicategory and the two category of free pseudoalgebras, these also have these tricategorical universal properties. So I guess that's the thing to say there. So the types of things that people are actually interested in applications, which are these Kleisli bicategories and two categories of free pseudoalgebras, they have these nice Kleisli universal properties. So they also have this this universal property here. Okay. So this is the last couple of slides. So I'll talk a little bit about some applications of this work and some further work that has happened since then and that is also ongoing. So one question that that I alluded to earlier was doing an analog of the formal theory of monads part 2, but now in the two-dimensional setting. So this would involve free co-completions now for these Tricategorical objects. Of course, you can just unravel the explicit description, and that has been done. But we don't actually have, as of yet, the universal property of this thing actually being a trico-completion, so that's still open. But nonetheless, given that explicit description, you can then go and apply that to the types of things that wreaths are used for in the ordinary setting. And so this has been applied to double category theory and also to categorical systems theory by Matteo Capucci and David Jasmyers. And then one last thing to say is that you can also think of monoidal versions of everything that I've said, and you can then think of, well, not just monoidal, but also braided, syleptic, and symmetric structures in the two-dimensional setting. And it's reasonable to ask whether such structures lift to Eilenberg-Moore objects for pseudomonads or extend to Kleisli bicategories. And so this has been looked at so for the Eilenberg-Moore stuff, that's in a preprint that's available on the archive, I think for about a year now. So that's there. And the Kleisli stuff, that's still being written up, but that should be on the archive soon, hopefully. I should also mention that the just monoidal variant, so not syleptic, braided, or symmetric, has also been treated in work by Philip Sappel and Hugo Poquet. And I should also say that for both the limit and colimit variants, so both the Eilenberg-Moore object and Kleisli object now, when you go to the monoidal setting, you're only going to get tricategorical universal properties, even in the limit with the limit variant. So there's some kind of extra complications that happen there, but nonetheless, these things lift and extend in exactly in a nice enough way for applications there. So I think that's pretty much the time that I have. So thanks everyone for your attention.
Great, thank you. Okay, we have some claps in the chat. Everyone's clapping. Okay, now people can now raise their hand and ask a question, or if you'd like to just unmute, feel free to do that. Great. I'm reminded of sampling morphisms. I guess from like in Markov categories, this epsilon map they call the sampling morphism, and I'd always kind of wondered like that. It just seemed such a universal thing to look for, this algebra structure.
Okay, well, that's very good for me to hear that this type of thing has already been kind of used or thought about, because I was looking around to see whether these kind of formal algebra structures had ever appeared. So maybe, yeah, okay. Is there a specific reference that you could get? Maybe you can send it to me later, but
for me, Paolo Perrone comes up, but I think if you look in NLab under sampling map or Markov category, you should find it.
Okay, great. Thanks. Yeah, I'll do that. Thanks.
Yeah, they have some probability distribution and they want to sample from it. Yeah, and so that's a map from A to S of A or whatever, but it's the identity, externally to identity. Okay, other questions? I guess mine was more of a comment. Okay, none are coming up. Sometimes what we do is people prefer to ask questions offline. So what I think we'll do, unless somebody quickly raises their hand, is that we'll turn off the live stream and the recording and then see if anybody has some more casual questions. I guess I'll do that now. Maybe. Okay. Okay. Oh no, Igor is raising his hand. I don't see that.